Good evening, everyone. My name is Aditya Sharma, and this is Fundamentals of Compressible Flow course being conducted by NPTEL, right? And we are into the ninth live tutorial session under this uh, course, right? And the topics we shall be discussing today are supersonic nozzles and then supersonic diffusers, right? And the instructor for this course is Professor Niranjan Sahu, right, from Department of Mechanical Engineering, IIT Guwahati. And I also am affiliated to IIT Guwahati only, right? I'm a research scholar there and also a Prime Minister's Research Fellow, right? Doing my PhD under Professor Niranjan Sahu only, right? And we shall start in another 4 minutes, I believe, right? So till then, let's wait if somebody joins. Uh, After that, we shall start today's session. Thank you. Okay, I believe we can start today's session, right? So, as I have already mentioned that we shall be discussing the supersonic nozzles and diffusers. So in this whole course, we have been studying various things, right, related to compressible flow. So in that series also we have done some preliminary discussions on what are nozzles and what are diffusers, right? So nozzles are basically to accelerate our flow, and on the contrary, diffusers are to slow down the flow in our hand, right? So this is fundamentally, basically, what is the function of a nozzle or a diffuser, right? So as we have been doing in previous tutorials, so uh, the session goes like this. So first of all, we discuss the topics that have been covered in the concerned week's lectures, right? So this is ninth tutorial related to week 9 of this particular course, right? So we shall be discussing the topics related to week 9, right? After that, we shall see some conceptual questions, right? And we shall discuss the conceptual questions, right? And then we shall discuss later in the session few numerical questions also, right? So there are, because there in your current assignment of this particular week, right, you have numerical questions also. So uh, those numericals that will be discussed, they will be useful in solving your assignment, right? All right. So let's move forward. All right. So first lecture in this week is based on isentropic nozzle flow, right? So we discussed in previous classes, this previous lectures of this course, this isentropic case, right? So first, uh, by isentropic here, uh, they mean that the flow in this nozzle is ideal, right? But which is not the case in reality. So we shall later also see, like in reality, what happens in these nozzles, right? But this lecture is based on this lecture is on the isentropic case of the nozzle flow, right? Okay. So first, oh sorry, right. So first topic in this lecture is shock waves and expansion waves and overview. So this is nothing but an overview of the shock waves, be it a normal shock, be it oblique shock, and then expansion waves also, right? So these two concepts, right? An overview has been given because we have already discussed these two topics in detail. So an overview just uh, has been given so that we can so that the this overview can prove handy for the later discussions in this particular session, right? So then the next topic is isentropic flow through a variable duct. So in initial lectures, this isentropic flow through a variable duct has was introduced, right? So there we saw how with the area. So if I can draw it, right? Okay. So this 24 week line, right? So I'll just draw a nozzle, right? So if you see, right? So here what is happening is with the passage of the flow in this duct, right? There is change in the area that this flow experiences, right, of the duct. So in such scenario, what happens, right? This has been discussed in this topic. This also, I believe, is a kind of a recap of the previous knowledge that we gained in the lectures, right? In the previous lectures, right? So in this topic also is this that how the flow is subsonic or supersonic flow behaves when we have a convergent section or a divergent section, right? So let's see if we have a convergent section like this. So in that case, if we have some kind of flow, right? So what happens to, let's say it is moving with Mach M, right? The same way, if we have a divergent section, right? So is if there is a flow this way, so if your M is subsonic or supersonic, in that case, what happens to your flow, right? As it proceeds in a duct, right? For example, if the flow is subsonic and we have a convergent section, in that case, there will be increase in the velocity of the flow, right? And for this divergent section, if there is a subsonic flow entering, in that case, its velocity is going to decrease, right? And the opposite is for the supersonic flows, right? So this was about the variable area duct, right? Then the next topic is isentropic supersonic nozzle flow, right? So in this case, we are concerned with basically with this supersonic flows only, right? So if we are using nozzle word here, it means that we want to accelerate our flow. Though the flow in hand is supersonic, still we want to accelerate it further, right? So this is the crux of this particular topic, right? So 20.3 and 20.5, I believe these are like these are same topics, but in 20.5 they have just given this points, right? This main points related to this particular topic, right? Supersonic nozzle flow. So in 20.3 they have discussed, right? Uh, in 20.3 it has been discussed, like this supersonic nozzle flow has been discussed, and in 20.5 the bullet points, right? The main points related to this topic have been listed, right? So if you see supersonic nozzle flow, right? So I'll just, I have drawn this, but I'll draw again here, right? So if you see super, I'll just draw another nozzle, I believe, something like this. Right, so this is the throat. This is the throat section. So if I draw the this static pressure graph along the this length of the nozzle, so how will it be? Let's see. So this is static pressure by total pressure, right? Let me draw first and then I'll discuss. So let's say we have three exit pressures, right? At the exit, obviously, of this nozzle. So this PE3 is less than PE2, right? And PE2 is less than PE1, right? So it starts at the entry, right? At the entry. This is our exit. At the entry, P by P naught is 1, right? So the static pressure and the total pressure are same at the entry. But as we, if you see, this is the convergent section, right? So what happens is as the flow moves in convergent section, so it starts to accelerate, right? And uh, because of that, its static pressure starts to decrease, right? But for a particular exit pressure, right? The case, it varies from case to case. Like the value of this exit pressure matters in this case, like how the this flow behaves in a nozzle depends a lot on the exit pressure of the nozzle, right? So if the pressure is as high as PE1, so you can see that the flow here has not reached its choked condition, right? For choked condition, we have this at throat P by P naught. From our previous knowledge, we know that it has to be 0.5 to it, right? But if the exit pressure is not sufficient, then flow doesn't choke, right? And when as the pressure, exit pressure is decreased, so there comes a point when the this flow in the throat starts to choke, right? So even if further this exit pressure is reduced, the flow will remain choked in that nozzle, right? So this is our nozzle, right? Isentropic supersonic nozzle flow. Then there is isentropic subsonic nozzle flow. This is nothing but if you see the PE1 and PE2 cases, right? So in that case, the flow hasn't reached the sonic mark, right? Even at the throat, the flow hasn't reached its sonic mark. So in that case, we call that nozzle as a subsonic flow nozzle, right? Because there is no sonic element in that, right? So that is isentropic subsonic nozzle flow, right? Then 20.5, I have already told it has similarities with 20.3. And after that, there are numericals related to this lecture, right? So this was about isentropic nozzle flow. And then there is adiabatic nozzle flow, right? So in this also at starting there are shock waves and expansion waves that have been discussed, right? And after that there is this isentropic flow through a nozzle. So it is the previous topic only, right? So these are the previous topics that have been discussed again, all right? Just to create a base for this particular lecture, right? And then there comes this adiabatic nozzle flow, right? So in this case, what happens is that we consider the real time flows, right? In reality, how the flows a particular flow behaves, a supersonic flow behaves in a nozzle. So that has been introduced in this topic, right? So because in reality this reversibility element goes out, right? And only the adiabatic component stays. So from that point of view it has been discussed, right? And then in that only there is next topic is normal shock formation. So we see at that in the divergent section of this nozzle we get to see normal shocks, right? So later when we will discuss the topics, I believe these questions, I believe, then we shall like I'll try to like graphically try to discuss this, right? So when there is a normal shock, how the pressure graph comes out, right? So I shall draw that, right? right? So for now only, just we have to remember that at the there are cases where at the divergent section we get to see normal shocks, right? So it has to do with the back pressure of this nozzle also, right? Right. So back pressure and the exit pressure, right? So when there is some particular exit pressure and we have this back pressure in hand, so how these two parameters uh, change the type of phenomena we see at the exit of the nozzle. So this we shall discuss, right? And then there is this over expanded case, right? So over expanded case, if I tell you, is nothing but when your exit pressure is less than your back pressure, right? So over expanded case is when your exit pressure from your flow, right, is less than your back pressure. So in that case, we get to see oblique shock waves at the exit of the nozzle, right? And then there is another case of with the, of this under expanded nozzle with these uh, nozzle flows, right? Adiabatic nozzle flows. So in that case, what happens is your exit pressure is greater than the this back pressure, right? So in that scenario, at the exit of the nozzle, we get to see a expansion wave, right? We get to see an expansion wave, right? Or should I say expansion waves, right? So this is overexpanded case, and then there is underexpanded case for nozzles, and then there is this difference has been shown between these two types of flows, right? This isentropic flow and the adiabatic flow, right? So these two types of flows, right? So how they are different has been discussed, right? All right. And then this complete sequence of flow inside a flow. So this has been summarized, right? Flows in a nozzle has been summarized, right? Taking overexpanded case into consideration, taking underexpanded case into consideration, right? Taking ideal expansion case into consideration when PE equals to PB, right? Exit pressure is equals to back pressure, right? All right. Okay. Then there are numericals linked to this lecture, right? Lecture 21. All right. So this was about your second lecture of this uh, week's content, right? So moving on to the next lecture, right? So the last lecture in this week's content is based on basically supersonic diffuser, right? So supersonic diffuser from the context that supersonic diffusers are used in supersonic wind tunnels, right? So they have a big role to play in supersonic wind tunnels. The reason is that we want to save the our total pressure, right? So we want to minimize the loss in the total pressure that the wind tunnel shall witness while in operation, right? So wind tunnel is basically a nozzle, a test section, and a diffuser, right? So if I just write here, first there is a reservoir, right? Then there is this nozzle, right? Then there is test section, and after that we have diffuser, right? And after that we have our exit. From here we have our exit. Right? So this is how these are the components. So these are the components of a supersonic wind tunnel and how the flow moves through it, right? So this is the sequence of it. So in it there is a reservoir, high pressure reservoir, right? From there we accelerate this gas, right, or air to this nozzle, and then this enters our test section where we have our test body, right? And then because we have accelerated the flow, then now we want the flow to decelerate because the speed at which the flow is, if at the same speed it exits into the atmosphere, the pressure losses, total pressure uh, loss will be huge, right? So to avoid that, a diffuser is used, right? And then the flow exits through this diffuser into the atmosphere, right? So in this lecture's content, the first topic uh, discussed is concepts related to a nozzle and a diffuser. So different concepts related to a nozzle and a diffuser have been discussed in this topic. And then this lecture comes into the supersonic wind tunnel. So I have already discussed, right, the main components of the supersonic wind tunnel. So a very uh, nice diagram also has been given in the lectures, right, of a supersonic wind tunnel. Right. And then there is this. Okay, then this topic again is supersonic flow in a nozzle. This again has been discussed. So a number of times this topic has been discussed, right? In the previous lectures also, and in this week's uh, first lecture of this week, right? There also it has been discussed. So after that, the focus comes on to the supersonic diffuser, right? Then because as I already mentioned that we want to reduce our losses, right, when we are running a supersonic wind tunnel. And for that case, we need to have good understanding of our diffuser part of the supersonic wind tunnel. So for that only, this discussion has been done in the lectures, right? So diffuser, the throat of the diffuser. So if you see geometrically, there are not major differences in a nozzle or a diffuser, right? So it also has a throat. This is what I mean to say. So in this first subtopic of supersonic diffuser, the throat diffuser throat has been discussed, right? So what dimensions of the throat we need and how this throat diameter is constrained in what way has been discussed, right? Right, and the efficiency of this diffuser, right, vis-a-vis saving our total pressure, right, or reducing the total pressure loss. So this has been discussed in this topic, and then this topic has been summarized, right? And later there are numericals based on this topic, right? So this was about the review of topics of week nine's lectures, right? Now we move on to the conceptual questions, right? Okay, just give me a few seconds, right? Okay, so let's discuss the problems, right? So for the problems in the previous sessions also, I have been doing this. So I write the topic to which the problem is related, right? So that we know to which topic we need to refer to and discuss this particular problem, right? Or a problem in general. All right. Right. So first question is on isentropic flow through a variable area duct, right? So the question says that irrespective of nozzle diffuser action in the passage, the flow is sonic at dash of the duct, right? This question we have done in the same, I believe, the question of same taste of same nature, right? We have done in one of the previous sessions, but because it has been discussed in this session, so there is no harm in again countering this question, right? So the flow is dash. So whether this duct is giving a nozzle action or a diffuser action, doesn't matter. Some part of this duct can be sonic in both the cases. So what is that part? So it's pretty straightforward, right? The answer to this question is B, right? So be it the nozzle action, right, where we are accelerating the flow, or be it diffuser action where we are decelerating the flow, right? So nozzle action, if there is Mach is less than 1 and we have a CD nozzle, right? And we have sufficient back pressure, right? In that case, the throat will choke, right? And at the throat, the flow will be sonic, right? And for diffuser action, if we have Mach greater than 1, so if we have a supersonic flow at the entry, right? So in the convergence section, our flow will decelerate, right? And at the throat, we will get sonic value, right? And then flow further decelerates in the divergent section also for the diffuser action, right? So the answer to this question is option B. Sorry, right? So let's see the next question. This was about a variable area duct. So B answer is correct. So the next question is from the topic isentropic supersonic nozzle flow. Right? So the flow is supersonic and there is nozzle action in it, right? So the question says that the Mach number at the exit of the nozzle, right? So Mach number at the exit of a nozzle is fixed by the area ratio. All right. Between dash and dash. Do we have options? Yes, we have 4 options to this question. Right? So what will be the answer to this question? So this question basically is from a expression, right? From a formula, right? So if you see, let's write down this formula, right? That's for question number 2. So we have this formula. Please let me know in the comments if there is some issue with this formula, right? if I'm making some mistake in writing this formula, right? All right, so this is our formula. So here A is the area at some section in the nozzle, right? In the direction of the flow. So if this is a nozzle, so at some location, right? At some location, maybe here or here or here or here. So at some location, this is area A, and A star is the area at the throat, right? These dotted lines. So at the throat, A star is the area. Then gamma is specific heat ratio, right? It's a ratio, Cp by Cv. And Mach, M is the Mach which corresponds to the area A, right? So it becomes, if this is the formula, if we have this general formula in hand, so for exit case, exit of the nozzle case, so this formula becomes this, right? So Mach depends on the area, two areas, right? The area ratio of this exit of the nozzle and the throat. And if we see our options, so it says entry and exit, then says entry and throat, right? So entry and exits. So there is exit, there is throat, right? But they are not coming together in some particular option. But if you see option number 4, so throat and exit, we have in a single option. Right? So if you see its answer, the answer is also D, right? So this was question number 2. That was based on isentropic supersonic nozzle flow, right? Now let's move on to next question. So next question is based on isentropic subsonic nozzle flow, right? So here the flow in the nozzle remains subsonic, right? Sorry. So question number 3 says below the exit pressure corresponding to choked mass flow rate, right? So there is some exit pressure related to choked case, right? So if I show you this graph, right? So here the 0.258 case is the choked case, right? We also know this from our previous knowledge also. And this PE3 is the exit pressure corresponding to in this choked case, right? PE3, okay, from this graph. So below the exit pressure corresponding to the choke mass flow rate, the flow properties at the throat. So the question asks about the flow properties at the throat and the entire subsonic section, right? So what is the subsonic section? Subsonic section is nothing but the convergent section. Why so? Because the flow is subsonic in that section, and at throat only it has changed to sonic. And further, if we go down the this nozzle, right, downstream of the nozzle, in that case the flow further accelerates if we have apt back pressure, right? So the flow properties at the throat and the entire subsonic section change with change in the exit pressure. So the question says that below the exit pressure corresponding to the. So the question tells you to remain below the exit pressure that corresponds to a choke flow, right? So the question is asking you to remain. So if this is P3, right? Sorry. So the question asks you to remain below this level, right? So if you are somewhere below this P3 level, right? In that case, if you change this exit pressure, so what will happen to the properties of the flow at the subsonic section and at the throat, right? So the question says that the change with change in the exit pressure. So if you change this exit pressure, right? So the properties in this subsonic section and this throat also change, right? And then the question has given two options. So whether it's true or whether it's false. So if you see the choked condition, right? For the subsonic section or the convergent section and the throat, below this PE3 level, there is not going to be any change, right, in the properties. This section is going to remains same as far as the properties, flow properties are concerned, right? But same is not the case for the divergent section, right? That is why we see things like uh, overexpanded case or underexpanded case, right? Or ideal expansion case, right? But for this particular scenario, there is no change, right? So the answer to this question is false, right? There is there should not be any change. Right? The answer to this question is B, false. So this was a question on isentropic subsonic nozzle flow, right? Okay. So let's move on to next question. So question number 4 is on isentropic conditions, right? And the question number 4 says a minimum area at the throat in a nozzle is a sufficient condition for the flow to be choked, right? Whether now option, if you see whether this is true or false, right? Yes. So if we have a flow, some flow if we are having in a nozzle, so in any case, if we have some minimum area, right, throat area, in that case, the flow is going to be choked. So whether this is true or false, right? So this statement is plainly false, right? Because for the flow to be choked, right, we need appropriate pressure ratios, right? So at the reservoir we have some pressure, and at the back we have some pressure. So if they are in correct states, only then, or if they are in viable states, only in that case the throat is going to be choked, right? Just by saying that we have some minimum area and we have some flow, so it is going to be choked based on just area, doesn't make sense at all, right? So B is the answer to this question, right? So let's move on to our next question of the session, question number 5. So this question is on adiabatic nozzle flow, right? Adiabatic nozzle flow, where we encounter normal shocks, right? At the exit, in cases we encounter oblique shocks. At instances, we encounter at the exit expansion waves, right? So, question number 5 says that in the adiabatic nozzle flow, there can be formation of oblique shock or expansion wave in the divergent section. Right? So in the divergent section, there can be oblique shock formation or divergent or expansion wave formation. Whether this statement is true or false. Right? So it's 4 p.m. already, right? So we'll take a break, right? 5 minutes break, and then we shall look into this question, right, in front of us. Let's take a quick break. Okay. Okay, let's continue with our session. So we were discussing question number 5, right? So this is an adiabatic nozzle flow case. And the question says that in the divergent section, there can be oblique shocks and expansion waves. So whether this statement is correct or not. So obviously this statement is not correct because we see oblique shocks when we have some compression corner, right? So if we have some concave corner, we see oblique shock, and in case there is convex corner, in that case we obtain an expansion wave, right? Or a series of expansion waves. But in the nozzle, we don't see any such thing, right? In the divergent section. So in that case, this statement is false, right? Right. So we will move on to our next question. The question is again on adiabatic nozzle flow, and the question says that across the slip line, pressure must be same, but the velocities can be in different directions. So I hope you all remember the concept of slip line, right? So when we were discussing the interactions of two oblique shocks, right? Or different types of interactions we studied in the previous lecture, right? So if I go into the notes of previous lecture, right? So we have these oblique shocks of same family, right? And then oblique shocks of different family. In these topics, we studied this concept of slip line, right? So uh, why there was a requirement to introduce this concept of slip line, because uh, there are this entropy differences across this slip line, but there are some common things across this slip line, right? But even after having these common things, because there are entropy differences across this imaginary line, in that case, we needed to define this particular thing, right? So the question says that, let's first of all read this question, right? So the question says that across the slip line, pressure must be same, but velocities can be in different directions, right? So from the previous lecture, we have seen that across the slip line, the first of all, the static pressures remain same, right? Because if there are pressure differences, there will be flow across the slip line. If across the slip line there are pressure differences, there will be flow, no doubt, right? So from that only we can say that across the slip line there will be no flow, right? but along the slip line, obviously there is flow. So the second statement is velocities can be in different directions. This is not possible in any case, right? Velocities cannot be in different directions. Velocities are along the slip line and in the same direction, right? In the both the sections of, right, of a slip line, right? On both the sides of the slip line, the velocities are along the slip line and the static pressure static pressures are also the same across the slip line, right? So if we see the options, whether this is true or false, this is a false statement, right? Okay, so let's move on to next question. So next question is based on normal shock formation in nozzle, right? So I was telling previously, right, that there is normal shock formation in the divergent section of the this in the divergent section of a nozzle, right? So how that happens, right? That we shall see, right? Right. So I believe now I should draw this. Right? I don't want you to draw. So I'll extend this graph only, right? Okay. So below this is something like this, right? This is our exit, right? This is our position in the nozzle, right? So what happens is, so if we further lower the this exit uh, pressure of this nozzle, right? So we start getting a shock, right? So up till this point, right? Up till this point, the pressure, your static pressure reduces, right? But after reaching this point, right, that I have marked, so it experiences a shock, normal shock, right? And in that case, your this static pressure obviously drastically increases, right? In comparison to the expansion that uh, the flow had experienced, right? because of normal shock, there is this drastic increase in the pressure, and the exit pressure reaches at this place, which is PE4, right? All right. So if we further reduce this, if we further keep reducing this exit pressure, right? So there a time will come when the this shock will reach at the exit, right? So we will see a shock at the exit. So this will look something like this, right? I'll just draw this in bold, right? So this will be, let's say, PE5. So PE5 is that exit pressure, right? Where the shock is standing at the exit of the nozzle, right? And what happens is if we further reduce the uh, exit pressure, right? So if we further reduce the exit pressure, in that case, we start observing oblique shocks at the exit, right? The diamond shape oblique shocks we observe, right? So which reflect as expansion waves from free boundaries that we have seen in the previous week's content, right? And if the exit pressure is beyond the back pressure, right? Its value is below the back pressure, then we call it as under expanded case, right? This is our PB scenario, right? So in that case, what happens is we get a under expanded nozzle flow where at the exit there is expansion waves observed, right? So now we see our this question, right? So the question says that let the sorry, it has to be B, right? So let there be a normal shock formation in the divergent section of the nozzle for an exit pressure. Okay. If the exit pressure is reduced further, the normal shock will move in downstream direction, right? So whether this statement is true or false, right? So I have just mentioned, right? So if there is this exit pressure PE4 where we are getting some normal shock, and if you see this PE5, right? So PE5 obviously from the graph also you can see that. So I have consciously kept PE5 less than PE4, right? So you can see that the shock has moved downstream and the exit pressure has also reduced with that, right? So if the exit pressure reduces, the normal shock goes downstream, right? So there lies the answer to this question, right? So it has been correctly mentioned that the normal shock will move in the downstream direction. So the answer to this question will be true. Right? So this was question number 7, right? Let's see question number 8. Question number 8 is from under expanded nozzle case, and it says in under expanded nozzle there is formation of oblique shock at the exit. Straightforward question, right? So what is an under expanded case? So I'm again drawing a nozzle, right? This is our nozzle, right? This is throat, right? This is entry, this is exit, this is throat, right? P by P naught, this is X direction, right? Okay. Now this is 1, right? And this is our choked condition, right? 0.528. Then there is some condition where there is this, we get a shock, right? But then there is condition, sorry, where we have this under expanded case, right? This is over expanded. This is under expanded. This is under expanded case, right? And here PE equals to PB for this case, right? So here P exit is yes, P here the P exit is greater than the P B, that is back pressure, right? That is why we are saying that it is under expanded, right? So in that case, we see that there is formation of expansion waves. This I have already mentioned. Just I had to discuss the graph corresponding to under expanded and over expanded more clearly. So that's why I drew that graph. Otherwise, answer to this is false, right? Because expansion wave. We see an expansion wave, right? In this case, we see an expansion wave. All right. So question number 9. Question number 9 is on supersonic wind tunnel. Right? And it says a supersonic wind tunnel. A supersonic wind tunnel is designed to compress a stagnant gas to supersonic speeds. So whether this question is right, true or false. So if we read this question very casually, so there are chances that we will make mistake in answering this question. The supersonic wind tunnel is designed to compress a stagnant gas to supersonic speeds. So if you see, yes, supersonic speeds has been mentioned, right? So it does something to stagnant gas so that it reaches supersonic speeds, right? But whether that process is called compression. So this word is very important to notice, right? If we wish to answer this question correctly, right? Because when we discussed shocks, there we clearly saw that a shock is a phenomenon by which we can compress, right? And what are the consequences of a shock? The major consequences that there is reduce in the velocity, right? Because of compression of the shock, there we see a decrease in the velocity, right? But here, sorry, here if we see the supersonic wind tunnel, there is increase in the speed, right, of the stagnant gas. So whether that is done by compression, no, right? The process is called expansion, right? The question is right in the sense, in its this aspect that the supersonic wind tunnel is used to increase the velocity of a stagnant gas to supersonic speeds, but that process is called expansion and not compression, right? So this question has B as its answer, right? Right. So let's move on to next question. Next question again is on supersonic wind tunnel, right? And the question says that how many throats are there in a supersonic wind tunnel, right? So that matter. Let's draw a supersonic wind tunnel, right? I believe we are in question number 10. So it is something like this. Here we have our reservoir, right? Then there is a nozzle, right? Then there is test section, right? Let's try to draw it more straight. Right. Then what is there? Then we have our supersonic diffuser, right? So this is throat 1, right? And this is our throat 2, right? This section is our nozzle, right? And this section is diffuser. And the middle section is test section, right? So this is our supersonic wind tunnel, right? So question asks how many throats are there in a supersonic wind tunnel, right? So option number B is correct. Right? There are two throats. One is of our supersonic nozzle, and then second one is of our supersonic diffuser, right? One is ahead of the test section and one is behind the test section or after the test section, sorry. Right? Okay, so let's move on to next question. Next question again is on supersonic wind tunnel. The question says that the performance of a supersonic wind tunnel depends on the performance of its, right? So four options are there. Yes. One is subsonic diffuser, right? Subsonic diffuser, right? So it means a divergent section, right? Then there is supersonic diffuser, that is convergent divergent section. And there is supersonic nozzle, again, which is convergent divergent section. Then fourth is none of the above, right? So I have discussed it in the early part of the session that when we are working on a supersonic wind tunnel, we need to reduce the pressure losses, right? we need to reduce the total pressure loss when the flow exits the wind tunnel. Right? So for that case, we use a supersonic diffuser, right? And this diffuser only defines the performance, to what extent we are able to save the losses in the pressure, total pressure, right, of our flow, defines the performance of a supersonic wind tunnel, and that is done with the help of a supersonic diffuser, right? That saving is done with the help of a supersonic diffuser. So B is the correct option to this question, right? Okay, then there is supersonic. Again, next question again is on supersonic wind tunnel. Okay, and the question says, in a supersonic wind tunnel, the first throat is larger than the second throat, right? So what happens is that when this uh, wind tunnel, supersonic wind tunnel is started, right? It has this nozzle, it has a test section, and it also has a diffuser. In the beginning, this supersonic wind tunnel gets a normal shock, right? And to accommodate this normal shock, right? It this normal shock we get in this nozzle, right? In the divergent section of this nozzle, and then to accommodate this normal shock, the throat area has to be larger than the throat area of this diffuser has to be larger than the throat area of this nozzle. Okay, all right. Only then it will be possible uh, for this throat to accommodate this nozzle, right? So when the question says in a supersonic wind tunnel, the first throat is larger than the second throat. So this statement, so because this is a true or false type of question, so first throat is larger is not a correct statement, right? The second throat is larger than the first throat, right? Okay, then next question. So next question is on supersonic diffuser, all right? So the question says that when the convergent part of the diffuser changes the flow direction at the wall, right? Okay. So if you see a supersonic diffuser, right? This is the convergent part, right? Convergent part. And this is the divergent part, right? So the question says that when the convergent part of the diffuser changes the flow direction at the wall, it encounters compression corners, concave corners, for which oblique shock waves are formed inside the duct, right? And the total pressure drops. It's across the oblique shock or normal shock, there are pressure losses, right? We know that, right? But does that happen in this supersonic diffuser conversion part of supersonic diffuser, that there is this, we have this concave corner and then this leads to oblique shocks. So we also know that with concave corners the flow moves towards itself and we get oblique shocks, right? So in supersonic diffusers also this happens, right? So from the, if we see a supersonic wind tunnel, and when this flow exits, the supersonic flow starts to enter the supersonic diffuser. In that case, the convergent section it takes as concave corners, right? And we get an oblique, we get oblique shocks, right? And later in the this supersonic diffuser, downstream of the supersonic diffuser, we just terminate uh, this whole process by a very weak normal shock, right? Because we don't want, as I have discussed, that we don't want the pressure losses, total pressure losses to be too high. That's why we don't prefer to have a normal shock at the beginning, right? Otherwise, pressure losses will be too high, right? At early stages, we don't want normal shocks. That is why we have first oblique shocks and then later termination mm, by means of a very weak normal shock, right? Of this whole process of slowing down the flow, of this whole process of slowing down the flow by, we terminate this by means of a very weak normal shock, right? So this statement is correct, right? Right, this statement is correct. All right. So this is about the conceptual questions, right? Okay. Now we will try to solve numerical questions, right? Okay. So there are few things that are in our hand, right? That are given to us. So this is about a convergent divergent nozzle, right? So reservoir pressure has been given, reservoir temperature has been given, exit pressure has been given, throat area has been given, right? Exit Mach number has been given, right? And the exit to the area throat ratio also has been given, right? And then what has been asked? So firstly, so this topic of these four numericals is isentropic flow through nozzle, right? So this question asks, question number 14 asks, calculate the exit area. So this is very straightforward, right? First of all, I'll just write down for question number 14 to 17 what has been given. P naught has been given as 12 atmosphere, right? T naught has been given as 520 Kelvin, right? P exit okay. P exit has been given as 0.525824 atmosphere, right? And then throat area has been given as 0.35 meters square, right? Exit Mach has been given as 5.3, and then exit area to throat area has been given as 22, right? Obviously, exit area will be higher than the throat area, right? Than any area for that matter, right? In a nozzle, right? And also gamma is 1.4. That I have not mentioned in the question, but we'll take gamma as 1.4 for this question, right? So if you try to solve this, question number 14. Okay, A exit by A star is 22, right? Implies A exit equals to 22 into A star equals to 22 into 0.35, which comes out to be 7.7 meters square, right? Okay. Okay. Then question number 15 solution. Let's first of all check the answer this question, right? So this is 7.7 only, but you guys also can confirm from your end, right? All these answers, and if there is some mistake in calculation, then you can let me know in the comments, right? Okay. Then there is calculate the exit temperature, right? So if we see, we have exit Mach is there, right? And stagnation temperature is also there. So I believe we can calculate T exit, right? Yes. So T exit by T naught equals to 1 plus gamma minus 1 by 2 m exit square, right? So minus 1, right? So this is 1 plus 1.4 minus 1 divided by 2, 5.3 whole square, right? And this whole minus 1. So if we solve this, this comes out to be 0.1511, right? which means T exit equals to T naught into 0.1511, which means T naught is 520, right? T naught is 520, 0.1511. So if I work this out, this comes out to be 78.57 Kelvin, right? So this is my answer to question number 15, right? 78.57. All right. Now let's see next question. So next question is calculate the exit pressure, right? So again we will use this these isentropic relations, right? So because they have asked exit pressure, so we have mag and we have P naught also, so we can do that, right? It's gamma by gamma minus, right? So P exit by P naught is equals to by 2, right? Minus gamma by gamma minus 1, right? So if we work this out, it just comes out to be 1.34 into 10 raised to power minus 3, right? And then P exit equals to P naught into 1.34 into 10 raised to minus 3, right? And P naught is 12 atmosphere. So if you multiply it by 12 atmosphere, what we get is 0.016 atmosphere, right? So this is our answer to question number 16. Right? Okay. 0.016. All right. So now we are into the last question of our this session. Question number 17 solution. So question number 17 says calculate the mass flow rate, right, in kg per second. Mass flow rate is rho a v, right, or rho a u, where u or v is velocity, rho is density, and a is area, right? So we have area, but we don't have velocity, but we have Mach, right? And if we can find out the speed of sound at exit, then we have velocity also. And to find density, we will use this ideal gas relation, right? Which is P equals to rho RT. We have pressure at the exit, right? From question number 15, we have temperature at the exit from question number 14. Sorry, we have pressure from question number 16, I believe. Yes. And we have temperature at exit from question number 15, right? And we can find out rho from that, right? So let's do it. So we know P equals to rho E R T E, right? P exit is 0.016 into 101325, right? Rho E we have to find. R is 287, right? TE is 78.57, right? So if we work out rho E, it comes out to be 0.0718 kg per meter cube, right? Okay. And mass flow rate, wait, but we have not found out AE yet, right? So speed of sound at exit, right? 1.4 into 287 into 78.57. Yes, and it comes out to be 177.67, right? Then Mach is velocity by, right? Then velocity is, which is 5.3 into 177.67, which is 941.65 meter per second, right? Okay, so we have, sorry, so we have velocity also, and we have rho also. Now we can calculate mass flow rate. Mass flow rate equals to rho E AE UA, right? So this is rho is 0.0718, and then A is 7.7, U is 941.6, right? And what we get is per second. Right? Okay, right. So this way we have come to the end of this session, right? So now I shall conclude this session, right? So we discussed the topics related to week 9 in the beginning, and then we discussed 13 conceptual questions, right? After that, we did 4 numerical questions, right? Based on supersonic nozzles and supersonic diffusers, and this way we came to an end to this session, right? And this was it as far as this session is concerned, session number 9. And we shall, for the next session, we shall again meet on Sunday at same timing from 3 p.m. to 5 p.m., right? Till then, bye bye, take care, right? And happy learning. Thank you.